When we think about torque, we need to think about rotational equilibrium as one of the key concepts. Rotational equilibrium is where net torque is equal to zero. This means that there may be different torques going clockwise and counterclockwise about some point, a hinge, but when we sum them all up, the net torque is zero. That is, the counterclockwise torques and the clockwise torques equal to zero when we add them and fight them against each other. Let's imagine two children playing a game with a teeter-totter, and they're trying to stand in a way that the teeter-totter is going to balance with them both on two sides. And let's say the children are different mass. One might have 20 kilograms and the other might have 30 kilograms. If the first child is standing 1.5 meters away from the center, where should the second child stand so that the torques are in balance? So we can do a simple torque calculation to figure out where the second child should stand so that they're in balance. Remember, the formula for torque is torque equals force times distance. There's two ways to write the formula that summarize the idea of rotational equilibrium. One of them is saying torque clockwise equals torque counterclockwise. The other way is to say that net torque is equal to zero. These are really saying the same thing. The first one is saying if we take the two torques, one's going clockwise, the other's counterclockwise, and they balance out. They're equal to each other. So there's no net torque. The other one is saying if we add up one of them positive, one of them negative on the same side, they would cancel out. I like using the first of these two equations for questions, so let's try that. So what's the clockwise torque in this case? The clockwise torque is child 1. The counterclockwise torque is child 2. Let's put in some variables to calculate the distance the second child should go. We write torque clockwise equals torque counterclockwise. So the force the first child applies times their distance away equals the force the second child applies times their distance. Torque 1 equals torque 2, basically. Plug in all those numbers. Remember, the force is the force of gravity, so we use mg, and we can solve for d2. If you plug all those numbers in, you're going to get d2 equals 1.0 meters. So that's how far away the second child should sit or stand. And if they do so, the beam's going to be in rotational equilibrium. The net torques are zero, and so it'll be kind of balanced like that. Let's do some more examples. Let's imagine a beam perhaps on a construction site, which is attached to a wall at one side with a hinge, and it is attached by a cable on the other end to hold it upwards. Somebody comes and puts a box with a certain mass on this beam. We say the mass is 1 meter away from the wall, from the hinge, and the plank, the whole length is 2.5 meters long. However, there's another piece. The question might say, this plank has a mass of 25 kilograms, and it's a uniform mass beam. The idea of uniform means evenly distributed, and we can just imagine it's the same thing as if the mass was coming from the middle. Technically, we call this the center of mass. The center of mass of this beam will be occurring in the middle of the beam. So let's draw a torque free body diagram. So we place the hinge on the far right there, and there are three forces acting on this beam that might create torque. The mass of the box is creating a force of gravity going downwards, but also the mass of the beam is creating a force of gravity. And we place this second force, the mass of the beam gravity force, right in the middle of the beam. So that's going to be a 2.5 meter beam. That'll be 1.25 meters away. The third force is the force of tension that the cable is applying upwards, right at the end of the beam. Okay, so we need to calculate the force of tension in the cable. That's what the question will ask us to do. And the right idea is that this beam is in rotational equilibrium. It's not moving, so we can begin by writing torque clockwise equals torque counterclockwise. There are two clockwise torques. That's the force of the beam and the force of the box. And there's one counterclockwise torque. That's going to be the force of tension. Now, for this problem, I'm just going to write down the distances that each of these three has from the hinge. It may be a bit laborious to do that in every question, but when we're learning, it's nice to be clear about everything. So the box has what? 1 meter away from the hinge. We say that the force of the beam is halfway along the beam, that is half the length of the beam away from the hinge, so 1.25 meters. And the force of tension is all the way from the other end, so that's 2.5 meters. So now that that's clear, we can put all these things into the formula, and we're going to try and solve for the force of tension. When I write all the variables down, it looks like this, and then I solve for Ft. This is what I get solving for a force of tension. I just plug these numbers into the calculator. So the force of tension in the cable is 240 newtons. That is the force that will create a rotational equilibrium in this question. Let's do one more example of rotational equilibrium. Let's imagine a swimmer on a diving board, and they're standing on the very end of that diving board. So we got to put some numbers here. Let's say the person has a mass of 50 kilograms, and this diver is 2 meters away from the first post. But this diving board has two posts, kind of concrete hinges, that are holding it down on the ground. And there's a little distance between them. That's 0.5 meters. So we want to calculate the force of tension on both of those two hinges. And the way we do this is two separate torque imaginations for rotational equilibrium. So to calculate the force on the first hinge, let's say the left one is the first hinge, we need to imagine that the second post is a hinge. Let's draw a free body diagram for that. So now we're imagining that the diving board is kind of like a teeter-totter with the hinge at the second post. So there's going to be two forces here. The first force is the force of gravity that the diver has. So there's going to be another force provided by the first hinge. And the first thing is, what direction will the force be in? Well, we need rotational equilibrium. This diving board is not spinning or rotating around the hinge, so we are in rotational equilibrium. The diver is providing a clockwise torque, so I need to give a counterclockwise torque to fight that torque to keep it in equilibrium. So I need to make sure that this force is going to be downwards, because it's on the other side of the hinge, to create a counterclockwise torque. Okay, so let's plug some numbers in to calculate what that force is going to be. So this swimmer provides the force of gravity. He's going to be 2 meters away. And the second force, we call force 1, is going to be 0.5 meters away from the hinge. Here are the numbers. When I plug them in, this is what I get. I get 1,960 newtons of force are going downwards at the first pillar. Now let's calculate the force of the second pillar. So we're going to do a very similar thing, but reimagine now that the hinge is not at pillar 2, but the hinge is at pillar 1. Doing that will allow us to calculate the force at pillar 2. Let's draw the free body diagram for that. When I draw the hinge at pillar 1, there are two forces left on this. There's the force of gravity from the swimmer. Now again, I need to think about which direction is the force going to be at pillar 2. And again, I think rotational equilibrium. Torque clockwise is equal to torque counterclockwise. The swimmer is providing a clockwise torque. So how do I provide a counterclockwise torque? In this case, the force has to go upwards because it's on the right side of the hinge. Okay, let's calculate that force. We say torque clockwise equals torque counterclockwise. So force of the swimmer times his distance equals the force 2 times d2. Now, there's a little important note here. How far is the swimmer away from the hinge? He's 2.5 meters because it has to go all the way from the very front, all the way to the very end. I get 2,450 newtons. It's often good just to stop and think about a question after we're doing it to make sure we understand what we've said at the end. So it's interesting that, firstly, these forces are not quite the same value because for the second one, the person's force is further away. He's providing more torque to the second hinge than the first hinge. His distance is further away from the first hinge than the second hinge. It's also interesting that these forces are in different directions. And this kind of makes sense to me. If I think about the second pillar, it's a little bit like the person is yanking downwards on the pillar with his torque, so the pillar has to push upwards. If I think about the first pillar, it's like a teeter-totter. and he's pulling downwards and you're on the other end. You have to pull downwards to counteract that force. So this has been about the idea of rotational equilibrium, where we say torque clockwise equals torque counterclockwise. In the next video, we're going to look at torque with some angles.